question asks for probability of y being less than or equal to 2. And the probability of y being less than or equal to 2 is what? Actually, y is defined as the maximum of these two random variables. So I am replacing y with the maximum of x1 and x2 to be less than or equal to 2. But you see, the maximum of these two random variables to be less than or equal to 2 means that both of these random variables should be less than or equal to 2 at the same time. So these two statements are equivalent. The fact that the maximum is less than or equal to 2 is equivalent to the fact that both of them to be less than or equal to 2. So which one is maximum? I do not care. Which battery has the maximum lifetime? I do not care. What I care is both of them to be less than or equal to 2, because in that case, the maximum is going to be less than or equal to 2. And because these batteries have independent lifetimes, I can rewrite this joint probability as the product of individual probabilities, which is the probability of x1 to be less than or equal to 2 times probability of x2 to be less than or equal to 2. And because x1 is exponentially distributed with lambda equal to 1 over 3, its cumulative probability at 2 is 1 minus e to the power minus lambda 2 lambda x, if you remember. So let me show you the CDF of exponential random variable, which was 1 minus e to the power minus lambda x. So lambda is 1 over 3 and x is 2. Therefore, we have 1 minus e to the power minus 2 over 3. And for the second random variable, the rate parameter is equal to 1 over 5. Therefore, that probability is 1 minus e to the power minus 2 over 5. And the result is the product of these values, which is 0.1604. So with approximately 16% probability, that clock is going to stop in 2 days, okay, with 16% probability. Now I am going to solve another question. So the distribution of the maximum of n independent random variables, which is going to be simply a generalization of what we are doing. Okay, the distribution of the maximum of n independent random variables, which is going to be a generalization of the previous question. This time, imagine now, the clock is not working with 2 batteries, it is working with n batteries. Okay, the device is going to stop working when all of the batteries are exhausted. And the batteries have independent lifetimes. Now, we define y here as the maximum of n independent random variables, and each of these independent random variables have their own CDF, fx1, fx2, fx3, so on and so forth. So suppose we are interested in the probability distribution of y, and the probability distribution of y is what? The CDF of y at x, which is the probability of y to be less than or equal to x. And because y is defined as the maximum of all of these random variables, we write maximum of all random variables to be less than or equal to x inside the probability statement. And you know, the maximum of these random variables to be less than or equal to x, we need what? We need all of them to be less than or equal to x. Or in other words, if the maximum is less than or equal to x, all of them will be automatically less than or equal to x. Therefore, we rewrite this probability statement as the intersection of x1 being less than or equal to x, x2 being less than or equal to x, and all other random variables to be less than or equal to x. Finally, we know that these random variables are independent from each other. Therefore, the probability of the intersection can be rewritten as the product of the individual cumulative probabilities, which indicates that the cumulative distribution function of the maximum of these independent random variables is equal to the product of the cumulative probability distributions or cumulative distribution functions of each individual random variable here. Now let us solve a question here. x1, x2, and x3. These are independent and identically distributed standard uniform random variables. So they are independent and identically distributed. What does that mean, identically distributed? So they have the same distribution. They are, all of these 3 random variables are following a standard uniform distribution with lower bound parameter equal to 0 and upper bound parameter equal to 1. So all of them are following the same distribution type. And y here is a random variable that denotes the maximum of these three random variables. Y is equal to the maximum of x1, x2, and x3. Okay? So the question is asking me, compute the CDF of y. So I can do that. I know that the CDF of y is equal to the product of the CDFs of all these three random variables because they are independent and y is equal to the maximum of these three random variables. And then it says compute the probability of y being greater than 0.5. So I have computed the CDF. Now I want to compute a probability related to that. In fact, I can calculate it by using the CDF. I can subtract the CDF at 0.5 from 1. Now, for part A, I say that the CDFs of x1, x2, and x3 is uniform. They are uniformly distributed. The CDFs are equal to what? Simply equal to x. Why? Because you remember, for uniform random variables, the CDF is defined as x minus alpha divided by beta minus alpha. And for alpha equal to 0 and beta equal to 1, what is the CDF? It is exactly equal to x, an identity function. So for standard normal distribution, where we have lower bound parameter as 0 and upper bound parameter 1, the CDF of all three random variables is equal to x as a function. But these three random variables are independent from each other. Though their distributions are the same, they are independent from each other. Therefore, the maximum of these three random variables has the CDF as the product of each three CDFs, which is x to the power 3. And we are going to compute the probability of y being greater than 0.5 as the probability of y being greater than 0.5, which is 1 minus the probability of y being less than or equal to 0.5, which is basically 1 minus the CDF of y at 0.5. And that is 1 minus 0.5 to the power 3, and it is equal to 0.875. Okay? So basically, that is how we compute the maximum distribution of a maximum of independent random variables. Either 2 of them or n of them, it doesn't matter. In all the case, we do the same. We are multiplying the CDFs, individual CDFs of each independent random variable to get the CDF of the maximum of these random variables.